Which one? Case 2. I'm sorry. So this is the equation, and equation showing on the left column. Okay, and that's the equations. And for the equation, you can see the diffraction, maximum diffraction here is in the middle column. The maximum diffraction, it has negative term, right? It basically has negative term in this table. Negative simply meaning that amount of the diffraction is downward, because you can see the force is applied downward. And here we adopt the coordinate system is xy like this. So simply negative means downward. Okay. And we look at the slope. For this example, this is the point here, and you can see the slope simply is this. We pick the point and we draw the tangent. And the orientation of the tangent that represents is a slope. For this case, that is originally, if this is a horizon, the sea level, we define as a 0. For anything, if that is going clockwise, we define as the negative. So that means for the case 2, the slope at the free end is negative. Simply indicate that orientation is in this sense. Orientation, that means it deflected from the sea level clockwise. The clockwise means negative. That's the sign convention. Okay. And the more troublesome will be on case 5. Case 5 is the example similar to what we have done from the beginning. So case 5 do involve a lot of the calculations. But here you can see once you know how to exercise the problem, the solutions. Basically here you can utilize the table. For example, on case 5, on the left column, it only shows you the equation for one portion. For the case 5, it only shows you the equation for x less than 8. So for example, say for homework or for testing or for any exercise, if you would want to know the diffraction equation on the other range, then simply just repeat our first example. Okay? Okay? So that is for this table. And again, you can see today I don't have time to go over the test, but I will give you the test on Monday as the first thing. So we have 10 minutes. I want to use the same loading, but apply to the different boundary conditions, and I want to give you more tests and see. So allow me to switch to. Okay, so for the same loading conditions, then so the same type of the beam, and under constant distributed loading, omega equal to constant. And here we apply to the simply supported beam. So the difference from here is simply the type of the support. So from here, again, we have the 4 equations, 1, 2, 3, 4, the same thing here. And now we have the 4 equations. The 4 equations simply applied. So here, the equations 1 to 4 apply. And now we fix the boundary conditions for this case. So now the boundary condition, that is the free end. No, that is simply supported. So here we can adopt this case. So that means diffractions equal to 0, and then the slope, the bending equal to 0. At this free end, we have diffraction, which is constrained the vertical displacement. And there's a no bending, this is free to rotate, so the bending equal to 0. The same thing here. And so here, this one is, the first one is regarding the geometry. The second one is about the force. Okay, just give us the some comments here. So here we have 1, 2, 3, 4 boundary conditions. Then we should be able to solve for the 1, 2, 3, 4 integration constant. So the boundary condition 1 at x equal to 0, this end, y equal to 0. So that means right now I'm fixing this one. So that means using equations, diffraction, right now I'm going to use equation 4. So that means here C4 equal to 0. And then for the x equal to 0, the moment equal to 0, then here I use equation 2. So equation 2 is about the bending. So here the bending equal to 0, so we're using equation 2, we can find the C2 equal to 0. Okay, and now we fix the two things, then we apply this side at x equal to L, the y equal to 0. So again, we use equation 4, that's about the diffraction. So here we utilize equation 4. 0 will be equal to, we simply plug in x equal to L, so that means minus omega 24 L fourth plus so why not here we can get out the C2, C4 equal to 0 here. C2, C4 equal to 0 here. Okay, and then x equal to L, then we have the moment equal to 0. So here we're using equation 2, so that means 0 equal to, using equation 2, that is minus omega 0 divided by 2 L squared plus C1 L. Okay, so therefore from here we have two equations, two unknown, we can solve for C1 and C3. C1 equal to omega 2 over L, C3 equal to minus omega L cubed. So therefore, EI y of x will be equal to omega 24 EI. And then we rearrange minus x fourth plus 2L x cubed minus L3 x squared. And if you be able to compare the handouts, which case, I think this should be the case 6. Right, and that's the equation here. Will I be right?
Yeah.
And so for this case, most of the time the people like to say, we like to find what is the maximum diffraction and where. So for this case, you can draw, because this is symmetric, so because it's symmetric, you can guess pretty accurately. The maximum happened at the middle. Okay. Or otherwise, if this wouldn't be symmetric, how would you calculate the maximum diffraction? You simply is this. You simply take the derivative to find the y maximum. Is simply you take the derivative y dy dx equal to 0, and then to solve for x, then this one simply we apply the calculus. If we want to find any function, so any function, if we want to find the maximum or minimum corresponding is called the x star, right? Then how to find this one? We simply take the derivative and set the derivative equal to 0, then we will find the place. So the same thing here. So we solve for x, and that will give you the position where the maximum or minimum occur. So simply is this. You don't need to do the derivative because here equation 3 already provide you the derivative information. So simply from equation 3 you set up equal to 0, then you can quickly answer these questions. Okay? Okay, so here they better utilize this appendix. And again, the appendix will be based upon my suggestion is this. For every single case, if you would have time, you derive from the very beginning, like this example, from the very beginning, and until see whether you can find the equations being listed on the appendix. Once you can get through everything, then you can apply this table to all the calculations.